Swayam Prabha. Digital India. Educated India.
Okay, so for ease of notation, what I'm going to do is I'm going to call delta theta as u. Okay, I'm just going to, so that I don't have to write that cumbersome delta theta every time, I'm just going to denote it by u. And this is what Taylor series looks like. Now, how many of you have seen this before? Okay, fine. So let me just tell you what Taylor series does, right? So what this Taylor series says is that suppose you had some value of theta, right, which is this. You have computed the loss at that value. Okay, this is what we did when we started off, and we saw that that loss was some 0.073. That was the first point that we started off from. Now you want to move by a small quantity. That means you want to find a new value of theta because you're not happy with the current value of theta. Now what Taylor series says is that if you make a small movement, and this movement is small because we have made sure that eta is very small, so you're making a small movement in the direction of u. So the loss at this new value of theta is given by the current value of the loss function plus the derivative of the loss function with respect to theta multiplied by this direction that you have, and then so on, the second derivative, the third derivative, and so on. Are all of you fine with this? I'll just let you see the formula. There's nothing to explain there, it's just a formula.
So we don't know what the function is, right? Then we literally find the plotting and figure it out.
Right.
So how can we find derivatives?
How can we find?
Derivatives.
Because we have taken a differentiable function. The loss function is a squared error loss, right? I just want you to stare at the formula. It's actually, you would have done this in the single derivative case, right? Where you have f of x plus h is equal to f of x plus h into f dash of x plus h square into f double dash of x and so on, right? Are you familiar with that formula? How many of you remember that? If not, just look at the formula. There's nothing great about this. I mean, there is actually, but there's nothing that you need to worry about. You can just look at the formula and it should be clear what it is. Okay. Now what you need to take away from here is that you had a value of theta, you had a loss there. Now you want to move from here because you're not happy with this value of theta, and you have a formula for computing what this new loss looks like based on the Taylor series, right? So what you need to look at is the left-hand side and the first term on the right-hand side. Okay. So left-hand side tells you the loss at the new value of theta, and the first term on the right-hand side tells you the current value of the loss at this current value of theta. And then you have certain derivatives which tell you how do you compute the new loss function. Okay, fine. So let's just go ahead with that. And now since eta is very small, eta square, eta cube, eta raised to 4 and all is going to be much smaller. So we're going to ignore all the higher order terms and only focus on the first order derivative. Okay, that means the first term and the second term in the equation. Now suppose someone gave you a value of u. And if this u is a favorable direction, what does a favorable direction mean? That if I move in this direction, the loss at the new value is going to be less than the previous value. That means u is going to be a favorable direction only if the following condition holds. The loss at the new value minus the loss at the original value is going to be less than 0, which is the same as saying that the loss at the new value is less than the loss at the original value. Is that fine? Okay. Now can you tell me when is this condition going to be satisfied? Just look at the first two equations, look at this condition, and give me a condition, give me an alternate condition. When the second term is less than 0. That means when eta into u transpose and that gradient of L theta is less than 0. Is that fine? Okay. Now eta is anyways a positive constant that we have taken, so I don't need to worry about that. So what this condition tells me is that u transpose into this gradient is less than 0. Okay. Now here's one thing that we need to cover now. How many of you know what a gradient is? Okay. How many of you know what a derivative is? Everyone raise your hands, even if you don't know. Okay. Suppose I give you the function x square. Okay. What is the derivative of this function? 2x. Okay. Now suppose I give you the function x square plus y square. Suppose I give you the function of x square plus y as x square plus y square. What can I ask you to compute here? Can I ask you to compute the derivative? Can I ask you to compute the derivative with respect to x? This is a function of how many variables? What are the two variables? So what can I ask you to compute? Partial derivatives, right? So what is the partial derivative of this function with respect to x? 2x. How do you compute the partial derivative? You assume that the other variable is a constant and you compute that. Similarly, I can ask you to compute the partial derivative with respect to y. Okay? So you know what's a derivative, you know what's a partial derivative. Now can you tell me what's a gradient? A gradient is the dash of dashes. No. Vector of partial derivatives, right? So this vector that you see, which is the partial derivative with respect to x and a partial derivative with respect to y, is called a gradient, right? The collection of all the partial derivatives is called a gradient. Okay, now suppose you had a function x square plus y square plus z square. How many variables does it have? 3. I'm going to say collectively, I'm going to refer to these variables as x, y, as theta. Okay? And then I'm going to call that this is a function of theta. Okay? Now suppose I ask you, what's the gradient of the function with respect to theta? What is your answer going to be? The partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So that's all a gradient is, right? It's just a collection of all the partial derivatives. Now, what is the function that we are dealing with actually? What was the L in this Taylor series? What function was that? Loss function, right? So the loss function, what was the loss function actually? Yi minus f of xi the whole square. So this is a function of what? Just as I wrote that this is a function of x comma y, what should I write in bracket here? X comma y. Should I write as a function of x comma y? What is f actually? F is a function of w and b, right? So the loss is going to change when I change w and b. So it's a function of w and b, right? So the function that we are dealing with is loss of w comma b, and it's given by this formula. Is that okay? Everyone fine with that? So now when I ask you, and our theta is equal to what? How did I define theta? W comma b. So now when I ask you the gradient of this, what is it that you're going to give me? Partial derivative with respect to w and partial derivative with respect to b. What's the dimension of the gradient? What's the dimension of the gradient? 2, right? How many parameters you have? That many dimensions, right? What was the dimension of this gradient? 3. And if you have m parameters or m variables, m, right? Is that fine? Everyone understand what's a derivative, what's a partial derivative, and what's a gradient? Is that okay? Fine. So this quantity here, it's a product of two dashes. Your options are scalars, vectors, matrices. It's a product of two vectors. What are these vectors? What is u? U is a vector which contains two elements. What are those two elements? Delta w comma delta b is the change in w, right? And the gradient of L theta with respect to theta is a vector which contains how many elements? Everyone? Which two elements? Partial derivative with respect to W and partial derivative with respect to B. Is that fine? Okay. So everyone gets this. This is a dot product of two vectors. Everyone gets that? This is a dot product of two vectors. You have seen dot products before? Is that fine? So the dot product of X and Y is X transpose Y. Right? Is that okay? Everyone is with me so far? Okay. So what have we done so far? We have defined a loss function. The loss function is a function of the parameters of your model. The parameters of your model are W and B. We are collectively referring to them as a vector theta. And now we can say that we want to compute the gradient of the loss function with respect to this vector theta. And why did the gradient come into picture? Because we started with the Taylor series. So why did we introduce Taylor series? Because we had the loss at a certain value of theta. We wanted to move to a new value of theta. And Taylor series gave us a neat value of computing the loss at the new value with respect to the old value. And why did we care about these two quantities? Because we wanted that this quantity minus this quantity should be less than 0. So you get the whole picture. Okay? Theta, W comma B, Taylor series, so that we can compare the two values. Gradients, because Taylor series has the gradients. And what are gradients? They are collection of partial derivatives. Is that fine? Everyone gets that? And with that, we ended up with the following condition that U is a good direction if the dot product of U with the gradient is less than 0. Is that okay? Fine. Now let's just go ahead with this condition, right? So this is the condition that we have. Now this is the dot product between two vectors, and I'm saying that the dot product between these two vectors should be less than 0. Now, what are the possible values that this dot product can take actually? What's the range of the values that it can take? Now let me make things simple for you. Suppose U and gradient, both of these quantities. Suppose there were unit norms. What does that mean? That magnitude is 1. Is it fine? Everyone is okay with this? If that was the case, what is the range of values that this product can take? -1 to 1. Why? What does the dot product actually give you? It gives you the dash of the dash between the two vectors. The dash of the angle between the two vectors. The cosine of the angle between the two vectors. Is that fine? What's the formula for computing the cosine between X and Y? X transpose Y divided by magnitude of X and magnitude of Y. But I said that assume that the magnitude of X and magnitude of Y is 1, so the denominator just becomes 1. So the dot product is equal to the cosine of the angle between them. So what's the range of the cosine? -1 to 1, right? Hence, if these values are normalized, it can take on values between -1 to +1. Okay, fine. So is this inequality fine? That the cos of the angle between them is given by this formula, and that lies between -1 to 1. Okay. So now, what did I want? I wanted that this numerator should be less than 0. Okay. Now, what's the best if I ask you to give me something which is less than 0? If you're very say if you are very good at your job, which value are you going to give me? You're going to give me the least possible value. Right? I'm saying that the dot product should be less than 0. How much less than 0 can it be actually? What is the minimum value that it can take? -1. Right? And when will that value appear? What's the relation between U and the gradient at that point? They are? When will the cosine of the angle between U and the gradient be -1? When the angle between them is? That means when they are opposite to each. How many of you have heard this phrase earlier? Move in the direction opposite to the gradient. Have you heard this before? Yes, no? Yes. So now do you get why do you say that? Okay. So this is why you say that, right? So all I'm saying on this slide is that when the angle between u and the gradient is 180 degrees, this product is going to be less than 0. Not just less than 0, it's going to be the most less than 0 that it can be. And that's exactly the condition that you wanted, right? So this product actually tells you how much is L theta greater than L theta plus u, right? How much is the old value greater than the new value? And you want this difference to be as high as possible, right? And that is going to happen when your u is at an angle of 180 degrees with respect to your gradient. Everyone gets this? Okay? That's why you move in the direction opposite to the gradient. That means you take your theta, you compute the gradient of the loss function with respect to theta at that value of theta, whatever vector you get, right? You add that to your original vector. Does that make sense? Okay, fine. So now let's come up with the final rule. So this is what the final rule is. And let me again go back. Does everyone get this? So let me just do it here. So what the rule which I had is theta is equal to the current value of theta what is this? A small step, right? I am going to move only a small step in that direction. What is this? Gradient of the loss function with respect to theta. I have to move in the direction opposite. So what should I do here? Plus or minus? Minus. Everyone gets that? If I do minus, that means I'm moving the direction opposite to the gradient. Is that okay? Right? Now this theta is what actually? W comma B. Okay, let me just write it this way. Can you fill this for me? Dou by dou W of L and dou by dou B of L. And this is just a compact way of writing the same thing, right? Because W comma B is theta. This is again theta. And this vector is nothing but the gradient of the loss function with respect to theta. Is that fine? Everyone gets this? Okay. So I can either write it as a single equation or I can write it as two equations as I have written here. Right? I have a separate equation for W, separate equation for B, right? And I could have written this as a single equation for theta. Is that fine? Okay. Now, what does so where gradient of W theta is equal to something, right? What does that mean actually? So what's the derivative of x square? 2x. What's the derivative of x square at x equal to 2? What's the derivative of f x square at x equal to 3? 6. So you get the difference between the two, right? So there's a formula which is 2x. And then when I ask you what's the value at a particular value of x, you'll substitute that value in the formula and you'll get that value, right? So that's what that means. So when you compute the partial derivative of the loss function with respect to w, you'll get a certain formula which will be in terms of w and b. So you have to substitute the value of w and b in that to get the derivative at that particular value. Is that fine? Everyone gets this? Okay. So with that, what we have is the following algorithm, which is the gradient descent algorithm. So I'm starting at the 0th iteration. I'll run this algorithm for 1000 iterations. At each iteration, I'm going to do the following. I'll take the current value of w, I'll compute the gradient, I'll subtract it from the current value, and I'll update the value of w. And the same I'll do for b, and the same I'll do for all the other parameters that I have, and I'll keep doing this for 1000 iterations. And while doing this, I'm assured that what will happen from one iteration to another? The loss is going to decrease, because that's exactly how I'm updating my parameters. I have derived that principally starting from Taylor series. Does that make sense? Okay, fine. So far what we have shown is that starting from some random values for w comma b, At each step, if we continue computing the gradient and update according to what the gradient tells us, then we'll be continuously reducing the loss, and there will never be a situation where the loss increases. That's what we have achieved so far. Now, what is missing in this story? What have I not told you? That will not happen, because that's exactly how we have, that's what we derived, right? As long as you keep moving the direction opposite to the gradient, the loss is not going to decrease. But in this algorithm, what is missing? Stopping criteria, I've said I'll do it for 1,000 iterations. What's? How do you know there's only one? That's a separate thing, but this will at least reach somewhere, one of the minima. That's fine, right? What we're talking about is slightly more advanced for this. But now, how do you know how to compute this grad of W and grad of B? Do you know how to do that? So let's do that, right? So what we'll do is, for our toy example, let's assume there's only one point, okay? Then the loss function will be given by this quantity. Earlier, remember that we had the loss is equal to summation I equal to 1 to capital N, but I'm saying I've given you only one training point. That means that summation will disappear, and I'll have this f of x minus y, okay? Now, what is it that I'm interested in? The partial derivative of this with respect to W. That means a partial derivative of this quantity that you see inside the bracket with respect to W. So let's try to compute that. So I just want to give you a feel for that this is actually easy, no matter how complex this function looks like, but it's very easy to do this. So this is where I'm going to start. Now inside the bracket I have x and y. Then how do I compute the derivative with respect to W? If I want to compute the derivative with respect to a certain variable, then that quantity should at least depend on that variable. Does this quantity depend on that variable? Fx is a function of W comma B, right? So I'll just treat Fx as a function of W. I'll just move the gradient inside. That means what I'm going to do is, what's the first step here? Suppose I want to compute the derivative of z square with respect to x, where z is a function of x. What will I do first? 2z into derivative of z with respect to x, right? So what will happen here? 2 into f of x minus 1, and then I'll push the gradient inside. Is that fine? Everyone gets that? Okay. What next? Dou by dou w of y is going to be 0, because y does not depend on, that's the true y which was given to us, right? That's a constant for us. And dou by w of f of x. What is f of x? 1 over. Is that fine? Okay. Now I'll just do this on the other side. This is of the form 1 over e raised to x. Or let me just say 1 over x. What's the derivative of 1 over x? What's the derivative of 1 over x? Minus 1 by x square, right? So what will happen is, you will get this, and then you will push the derivative inside. What you have inside is of the form e raised to x. What's the derivative of e raised to x? E raised to x, right? So I'll have e raised to x, and I'll put the derivative inside. And now I have something very simple, because b is a constant. And what's the derivative of minus wx? Minus w, right? So this is what I'll have. Okay. Now can you simplify? What's the first quantity here actually? I'm talking about, there are 3 terms in this product here. What's the first term actually? It's f of x, right? It's minus f of x, right? Now just take my word for it that the second term is actually 1 minus f of x. If you go back, you can go back and work it out. So we have this simple formula, f of x into 1 minus f of x into x. Okay? So that's the partial derivative of the loss function with respect to x, with respect to w. Is that fine? Now this is the case when I had only one point. If I had many points, what would it be? So remember, my loss function was summation over all the n points and many terms inside, basically n terms inside. What have I computed here? I've assumed there's only one term which remains. All the other terms I've removed, because I assumed there was only one data point. And I've computed the derivative. If I had all the n data points, what would happen? Sum of derivative of a sum is sum of the derivatives, right? So I'll just have the same formula and sum over all the points. Is that fine? How many of you get this? Okay. Now, this is the partial derivative with respect to W. Without even computing it, can you tell me what is the partial derivative with respect to B going to be? It's going to be the same except the last x would not be there, right? Why? Because in the formula you have wx plus b, right? So w had an x associated with it, b does not have that. So the last term will be 1, everything else will remain the same, right? So I'll not derive it, I'll just write it. Okay? Is that fine? So now I have a value. What do I have? I have a formula for computing the derivative with respect to w and the derivative with respect to b. Now if I ask you the derivative at a particular value of w comma b, what are you going to do? Substitute the value of w comma b in this formula and compute that value. Is that fine? And what about x and y? What is the value for x and y that you will substitute? The data points which are given to you, right? So that means if I give you the value for w comma b, you can give me a number back because everything else has values. Xi has a value, yi has a value, and w comma b also has values. So you can give me a number back. Is everyone fine with this? Okay, fine. So now let's write the gradient descent algorithm. So what I'll do is I'll start with the data points which I have, x comma y. So the x's were 0.5 and 2.5 and the corresponding y's were 0.2 and 0.9. Then the first thing I'm going to do is I'll write the formula for computing the sigmoid function, okay, which is just 1 over 1 plus e raised to minus wx plus b. So if you're familiar with a bit of NumPy, then you will understand this. Or just take my word that it's the sigmoid function. Then what I'm doing is I'm plotting the error surface. How do I compute the error? It's the sum of the squared loss for all the data points. How many data points do I have? 2. So for all the data points, I'll compute what f of x is. I'll subtract y from it, square it, and then add it up. Is that fine? That's exactly what this piece of code is doing, right? And once I have this error, I'll just plot it for all the points. This plot is only for illustration. In practice, I'm not going to plot it because it's infeasible to do it for all values of x comma y, right? But I've just plotted it for showing something. Then I'll compute grad of b, which I just gave you a formula for doing, right? Then I'll compute grad of w. Again, we just saw a formula for this. Everything in this formula is known. And then I'll just write the main loop for the gradient descent algorithm, which is for a certain number of epochs or iterations. I'll go over all the data points. I'll compute the gradients. I'll add them up. And then I'll change my value of w as the last 2 steps, right? W is w minus eta into the gradient, and b is b minus eta into the gradient. And I'll run this algorithm for 1000 iterations. So let me just run this algorithm starting from some random point and see what happens. Okay. So you see the black point there at the bottom. What's that black point? That's my initial value for w and b, right? And I have just taken minus 2 comma minus 2 as the initial value. And what's the red point on the surface of the surface of that carpet? That's the loss value computed at that value of w comma b, right? Now what I'm going to do is I'm going to run this algorithm, keep updating my w comma b. So I'll see a different black point at the bottom. At every value of w comma b, I'm going to compute the corresponding loss function also. Okay, so let's see what happens. So I'm running it for a certain number of iterations. So see what happens. I keep changing my w comma b. At every point, the loss by guarantee decreases, and it continues to decrease till it falls into the valley, and now it will slowly decrease and reach the value of 0, which is the dark blue region. Is that fine? Everyone gets that? Okay. So that's all for today, I guess. We'll continue tomorrow. So what we have done so far is we have taken a very shallow neural network, which is actually just one neuron. We just had one sigmoid neuron, which had only 2 parameters, w comma b. We set up a loss function, we set up a training data, and then we learned the parameters of this sigmoid neuron, which is w comma b, with the help of gradient descent. And we came up with this principled algorithm which ensures that at every time step, the loss continuously decreases, right, until you reach the 0 error condition. Is that fine? Now what we need to do next is, from this sigmoid neuron, go to a collection of neurons, which is a feed-forward neural network, which will have several neurons in it, and then just extend this algorithm so that we can learn the parameters of this deep neural network, where the number of parameters would be much larger than just 2 in this case. Okay, so that's what we are going to do in the next lecture. Okay, thank you.